This is A-Level Physics lesson 36. And when we look at equilibrium rules, we are looking at the two situations we've been looking at throughout this whole topic. We're looking at what happens when the resultant force is zero and when the resultant moment is zero. That's it. And I could finish this lesson there, but let's just go into it in a little bit more detail. First of all, we need to be able to draw free body diagrams, or free body force diagrams. So in free body diagrams, an object is represented as simply as possible. We don't spend ages drawing a nice pretty object. We would usually just represent an object in a simple geometric way, maybe squares, triangles, circles, that sort of thing. So let us draw a free body diagram for a car which is on an incline. So we've got two wheels, and I'm going to cheat slightly to make the two wheels the same size and shape. Otherwise, there's no way I'm going to get the two wheels to be the same size and shape, no matter how hard I try. There we go. Two wheels. In fact, let's do them slightly further up the ramp. And I'm including the wheels because that's going to be important for considering the point of contact. Everything else can just be represented in this car by a simple rectangle. I don't have to make a lovely artistic diagram of a car, but this will do. It does the job. And in your free body diagram, you're drawing the forces, so we can go ahead and label the weight of this object and make an effort to draw the weight of the object, force arrow starting where the force is acting. It doesn't need to, but on a free body diagram it can be helpful. And we can label that W. Then we think, what other forces are acting? Well, there are two support forces that are acting on the wheels, the way I've drawn it here. Now, the way I've drawn it here, because the car is on an incline, maybe it's going up, maybe it's going down, it doesn't matter. Let's say it's going up. The two front wheels are each going to take half of the force that's on that front axle, and the two back wheels half of the force that's on the back axle. And so because of the symmetry along the width of the car, we don't really need to worry about that. So we could draw our two force arrows here. Now, these are support forces. These are contact forces. And contact forces, support forces, push forces are always normal to the point of contact, or normal to a tangent at the point of contact. So there's one of them. The other one would be there. And as we discussed before, it would actually be slightly longer arrow because it's, well, I don't know about slightly, it'll be a longer arrow because it's a greater magnitude of force. Okay. And we can label these two, the support forces, S1 and S2 perhaps. And you'll notice that S1 and S2 are both perpendicular to the slope. And that's because the point of contact with the slope, because it's a flat, well, how do I describe it? It's a straight line, it's flat. I know it's an incline, but it's still not curved, it's still flat. So the S1 and S2 are both going to have to be perpendicular to that flat incline. And this is also true if you've got a round object interacting with a round object like this. Perhaps this one's moving in this direction, this one's moving in this direction. The point of contact, the first one's going to push the second one that way, and the second one's going to push the first one that way, because the forces are always normal to the point of contact. So two circular objects you have to be careful of, but one of them is flat line. It's quite easy. And lastly, we're going to have the forces of friction. Well, let's say this object is stationary. Let's say it's parked. This car is parked on an incline. In that case, there is going to be a friction acting up the slope on the first wheel. Let's call it wheel 1 at the top. And I tend to draw these slightly away from the incline so you can see them a bit more. And there's going to be a force of friction there. Now, the thing about those friction forces is that they depend, they change, they depend on the other forces that are acting. So there are different, let's say, types of friction. There's static friction, and there is what we can call kinetic friction. Sometimes it's called dynamic friction. I'll stick with kinetic friction because that's what it tends to say in some of these textbooks, but I think dynamic friction is fine as well. So static friction can have any value up to some maximum. Then beyond that, what happens is the object is no longer stationary relative to the slope in this case. So you make the slope steep enough, the car will start slipping down it. At that point, you've got kinetic friction, which depends, usually, not always, but depends on the relative speed between the two surfaces that are in contact with each other. That's usually think about friction as one surface in contact and sliding over another. That friction usually depends on that speed, but not always. The dependency is interesting, and I'm not going to go into it now because it's not straightforward. But it will be less than the static friction, the maximum static friction. Now, calculations of maximum static friction, they tend to occur in A-level mathematics and not so much in A-level physics. A shame, but that's the way it is. So when we say this body is in equilibrium, we are saying that the vector sum is equal to 0. So we could say vector in equilibrium, vector sum of W S1 S2 F1 and F2 will be equal to 0. Now, what does that mean? That means that if we drew all 5 of those arrows in the way that we did quite early on, I mean, which lesson was it? Let's just go back a few. Here, so we drew A plus B and we got C, and we were looking at equilibrium then. If we did the same sort of thing, adding up our vectors, a vector sum, drawing our vectors the way we did back then what we would find is that we get a closed shape. So a force diagram, force vector diagram, shows a closed shape. In this case, some sort of pentagon, I guess. If we've only got 3 forces, then it will be a triangle if we're in equilibrium. It's going to be a quadrilateral if we've got 4 forces, and so on. And if you need to calculate what one of the forces are, you draw the diagram, and the missing one is the one you're looking for. So that's the first thing. Equilibrium, vector sum of forces is equal to 0, closed shape. But we can also break down vectors down to perpendicular components. Pen stopped working. There it is. Perpendicular components. And then each of those perpendicular components will also equal 0. So the components that are parallel to the slope, so that's F1, F2, and the parallel component of W, they will all equal 0 when added together. And the components that are perpendicular to the slope, so S1, S2, and the perpendicular component of W, they will also add up to equal 0. So break down into perpendicular components, I would say, and equate. Is that how you spell equate? Kind of looks right-ish. Equate to 0 separately. Now that can be more useful rather than trying to draw a force diagram, a scale diagram in A-level physics to look at perpendicular components. So you can do a scale diagram, or you can break down into components. So let's just have a look at that. Let's say that this is theta. like that. And we've done this quite a few times by now, so that should tell you just how important this is. The grey line I've just drawn is perpendicular to the inclined ramp, and therefore this angle here is also theta, must be. And so this is going to be right angles. So we've got our little triangle there. And we've done that because we can see that W cosine theta is the component that's parallel with S1 and S2, and W sine theta is the component that's parallel to F1 and F2. So we can then say that the vector sum of W plus, actually let's not say W, let's say, let's not do it as vectors, let's say it's scalars. So S1 plus S2 must equal W multiplied by the cosine of theta. Actually, we should be a minus in there because it's in the opposite direction, and when you add them together it should equal 0, but it doesn't matter. And we can also say, so that's when we're looking perpendicular to the slope, we can also say that F1 plus F2 is going to be equal to, in magnitude and opposite in direction, so again there should be a minus sign here, W sine theta. And that's it for the first condition of equilibrium. Now that is true whether it's an unstable equilibrium, a stable equilibrium, or a neutral equilibrium. In the case of something that's just rolling along at a constant speed, then that's a neutral equilibrium. This is all still true. If the object is accelerating, then it's not in an equilibrium because we are accelerating. So the resultant force is not 0. So this car on this ramp could actually be sliding down the ramp. It could be sliding down the ramp as long as the resultant forces in the two different perpendicular directions, parallel to the slope and perpendicular to the slope, as long as the resultant force is still 0, it's going to be sliding down the slope at a constant speed. It's not accelerating, and therefore it is still in equilibrium despite it moving. Really, really important. Okay, equilibrium does not mean stationary. Misconception. So that's the first thing. The second condition for equilibrium, the second rule for equilibrium, is the idea that the resultant moment is 0. In other words, we can say the principle of moments applies. Principle of moments applies. So in that case, if we take a pivot, we can take the same diagram and make it slightly more complicated, and we can use the same letters. So let's just duplicate that, take that, plop it down here. I'm going to modify it in a second. There we go. We could say that if we pivot it at some arbitrary point, remember it doesn't matter where we pivot, we could choose to pivot it anywhere. But let's pivot it here, then straight away F2 and S2 no longer factor in our calculation. We can get rid of them, we don't care about them. And F2, don't care about that either. I might have to zoom in with this, so let's, yeah, and let's go into here. Let's get rid of that one. Delete, and let's get rid of that one, delete. There we go. So now we can look at the moments situation. And, well, what can we see? Well, actually, F1 is also not contributing to the moment, because F1 is also, the line of action of F1 is also passing through that pivot. You see that? Anything that passes through that pivot, and F1 is one of them, the line of action of F1, the line of action of F1 passes through the pivot. So let's delete that, delete F1, delete that, delete that. So all I've done here, all I've done is delete the forces fit to width, lock it. There we go. I've just deleted the forces that are not contributing to the moment around that pivot. And then I can add some more stuff on. So let's get purple, we need a different color. And let's say we've got some distance here. Let's label that x1. And we've got some distance here. We could label that xw or something, I guess. I don't even know what I'd label that. Doesn't really matter what we label it. So let's call that x1, the distance to 1, and let's call that xw, the distance to the center of mass. xw, like that. Just choosing a notation that's going to be useful. So if the principle of moments applies, what have we done here? We have not drawn forces that do not provide moment, perhaps, or produce moment around the pivot. Or the fulcrum, as it's sometimes called. So you can see the two diagrams are the same. They're the same diagram. But S2 doesn't matter. F1 and F2 don't matter. So now we can say that the two different forces that are there are providing moments that are both going to be contributing to the resultant moment of 0. So x1, s1, that's the clockwise moment about the pivot, must equal to xw and then w, but it's not w. It's the component of w which is perpendicular to the ramp, because that's the one that's perpendicular to xw. Is this component there that we're interested in. So that's going to be, in this case, how we're doing it here is going to be w times the cosine of theta. So we now have 3 equations. And we could have set up the pivot in a different place and got another equation. And we can end up with 4 equations if you pivot it around the front wheel. So we could say, if pivoted at other wheel, what would it look like? Then it would look like, so S2, x1, S2 would be the same thing, wouldn't it? It equals, but then that's the line of action is going to be the same thing. So I think xw, if it's directly between the two pivots. So let's say it's x1 minus xw multiplied by, it's still the same thing. So it's still going to be cosine w cosine theta. So I'm just looking at this diagram. All I'm doing is looking at that diagram and thinking, okay, clockwise moment, anti-clockwise moment. Let's equate them. And we end up with something that looks a bit like that. Let's move it down a bit so we've got a bit more space. So what we've actually got here now are 4 simultaneous equations. They are all true at the same time. So here are 4 simultaneous, don't know how you spell that, equations to solve. And I don't know what we might be given in the question, what we might not be given. It might be given S1, S2. There are, what variables are there? S1, S2, X1, XW, W, F1, F2. So that's 7 different quantities. So we would need to be given 3 of those quantities, and we could calculate the other 4 by using these simultaneous equations. Oh, and theta, 8 quantities. There we are. So there are 8 quantities there. Let's just make a list of the 8 quantities. So quantities, we've got S1, S2, F1, F2, we have got F1 and F2, haven't we? Yeah. W, they're the forces. Then we've got X1, XW, and theta. I think that's it. Yeah, that's all the quantities that we have, all the quantities that we have and all the quantities that we need. So if we were given any 4 of them, then we could solve for the other 4. And I'm just going to make a note of that. If any 4 are given, the other 4 can be calculated using those 4 simultaneous equations that we've got. So S1 plus S2 using S1 plus S2 is equal to W cosine theta. We've got F1 plus F2 is equal to W sine theta. We've got X1 S1 is equal to XW W cosine theta, and we've got X1 S2 is equal to X, pen stopped working, X1 minus XW W cosine theta. And that should be straightforward then, solving simultaneous equations. You plug in what you know, you try and simplify and combine the equations as much as you can until one of the other quantities drops out, and then you plug that back in, find another one that drops out, and so on and so on and so on and so on. We're not going to do that now, mainly because you won't have to do this in A-level. This is how complicated it can get, but you won't need to do this. It's interesting, it's fun. You're not going to need to go into this sort of detail. But I don't know what you will have to do. I don't know what questions you're going to be given. There's no way we can predict that sort of thing. And you've got to be fluent in using the mathematics and having an idea of these 2 conditions of equilibrium to solve any sort of equilibrium question. So I'm going to leave this lesson there. And next lesson, we are actually going to have a look at a few questions from a textbook. Now, hopefully this is going to be okay for me to show this. Hopefully I don't get a copyright strike on this. We're going to have a look at some questions from a textbook, maybe not all of them, it's quite a few of them, just to see how you can solve these questions, equilibrium questions, statics calculations, using these principles.